Yes, class, we have discussed about the theory of the AVL tree, that is different type of possible solution for as a rotation when the height of the AVL tree uh, is imbalanced. Now today we will first take an example that how an AVL tree can be formed. So let's start with some arbitrary values. For example, if we start with some value which is a continuously increasing, something like that. Like if we have something like 1, 2, 3, 4, 5, 6. So if we consider creating a BST, it will look something like 1, 2, 3, 4, 5, 6. Right. So if we have a BST, it will be something like this, and which is not expected because ultimately we have seen that the height of the tree is not following the order of log n. That actually was our prime goal for converting our data structure from linear to non-linear. So that's why we will go for the AVL tree, right? So if we consider now AVL tree, we see that every time we have to think about, we have to take care about the height, the balance factor actually. So if we just put only a single one. So you see, this is the only node and it doesn't have any left and right, so left height of the left subtree is 0, height of the right subtree is 0, so 0 minus 0 is 0, right? It's 0. Now see, when you will insert 2, you want to insert 2, obviously 2 will be inserted in the right of 1, that's true, but at that time this balance factor will change. So it in the last day that we have seen an example of AVL tree, and we have calculated the balance factor. It is not something like we will create the whole tree and then we will calculate the balance factor and then we will correct them. It's like the insertion of a node in a binary in a tree. At the same time, the order is that we will insert the node in the BST in a existing tree first, in the existing AVL tree first. Then we have to calculate the balance factor of all the nodes, and according to that, those node which uh, which violates the rule of the balance factor, those nodes we will try to rectify. And if we find there are more than one nodes in a AVL tree which has violated the balance factor, in that case we will first try to rectify the nodes present in the higher level, then we will go for node present in the lower level. Now generally it seems that if you rectify the balance factor in the higher level node, automatically the lower level node balance factor is rectified. So we can maybe we will see these what I am saying here, we will see in this example or maybe other example also. Let's see what happened. So this is about inserting 1. Now when I will insert 2, we have to draw the tree again because the balance factor will change. So you cannot write balance factor and then cut, then write, then cut like this, right? So you should create the you should create the tree. As you will connect to a node, you have to recreate the whole AVL tree. Like after connecting these two, the tree will be something like 1 followed by 2. Now this is the tree. So the change from this one to this one like this, and here the balance factor of 2 is obviously 0 because it is the leaf node, and balance factor of 1 is now 0 minus 1, that is minus 1. Similarly, if we put 3, that means this one will be something like 1, then 2, then 3, and obviously balance factor is 0 over here, then 0 minus 1, that is minus 1, and this is 0 minus 2, that is minus 2. So here we can see the balance factor is validated in this side here. So as soon as the balance factor is validated, we have to rectify that first, and then we can proceed for inserting the other key values. So let's see what type of case, under what type of case it is. I mean, if you are able to remember what we have done, what the cases we have visited in the last day, then I hope you can easily understand. By the way, if you still have any doubt, or if you forgot about the different type of cases that we have discussed, you can go back to my previous video and check it, okay, in my YouTube channel. Now you see, in this particular situation, I can say that this particular node which become unbalanced is actually right subtree is heavy. The left subtree of this one is not heavy, the right subtree is heavy. Now right subtree is heavy, fine. Now what side of right subtree is heavy? The right side of right subtree is heavy, right? Because left subtree is, there is nothing. So that means this is under case of right subtree right heavy. Now if you go back to the cases and their solutions, you will see that in case of right subtree right heavy case, we actually do a left rotation with respect to the unbalanced node, that is this one. So we will have a left rotation something like this. That means the new formation of the nodes will become, if you have a left rotation here, it's something like 1 will come down and 2 will go up, as well as 3 will go up. So the new formation will become 2 will now become root whose left side contain 1 and whose right side contain 3. Now you see the balance factor of this one is 0, the balance factor of this one is 0. We have to calculate the balance factor again. After rotation we have to calculate the balance factor again. If still there is something to rectify, we have to rectify that. Anyway, so in this case we will see that there is nothing to rectify because balance factor is 0 for both, and here also in the case of root we have only one node in the left subtree, only one in the right subtree, so 1 minus 1, that is also 0, which is within the range, right? So that's why, that means this is okay. Still now this is okay, fine. Now I can try to insert this 4, right? So if we let's insert 4, that means we had a situation something like this. So this is our situation. Just in the previous, let's just write the situation again to keep the reference of the previous slide. Like this, so 0 0 and 0, and now we will try to insert 4, and you see 4 will be inserted in the right of 2, again here 3, so it's a right of 3, that means somewhere here. So that means new formation of the tree after including 4 will become something like 2 1, the right side 3, and in the right side of 3 it will become 4, fine. Now see, this balance factor of this one obviously 0, it is leaf node. This one is also 0, fine. And balance factor of 3 is what? It's 0 minus 1, that is minus 1. Balance factor of this one is what? It's 1 minus 1 2, that means minus 1. So still it is within the range, right? So that means, I can proceed more, like that means if we now insert what? Insert 5, we have to insert 5 and 6 again. So that means after inserting 5 here, the new formation of the tree will become something like In this side we have 1. In this side we have 3. In this side we have 4. In this side we have 5. So balance factor is 0 naturally for 5. This is for same for 1 also. And balance factor of for 4, the 4, this is what? 0 minus 1, that is minus 1. Balance factor of this one is what? 0 minus 2, right? So it's minus 2. Balance factor of this one is what? 1 minus 1 to 3, that means 1 minus 3 minus 2. You see the situation that I was just said of maybe 5 or 10 minutes back, that same thing is happening. That I have a situation where more than one node is unbalanced. So naturally question will come, which should be rectified first. As the rules say that you should rectify the higher level node first, that means I have to rectify the node 3 first. And then I will consider for the node 2 if required. So forget about node 2 right now. Just forget about the other part of the tree, the whole part of the tree. Only consider this is the part of the tree. And you see, this is the same situation we can see. Actually, the same situation happened because this set of numbers is in increasing order. That's why always it will come in particular case. Just for an example, I have shown you. So that mean what we can do? We can do a right subtree right heavy case, right? Okay, so that mean the rotation will be somewhere here. So that means after rotating, in the left rotation, the new formation of the tree will become. You see, this part remains same. Whatever tree present in this side doesn't matter, remains same. So 2 and 1. This part remains same. What will happen in the right of 2? Since this 3 has been, the rotation has been done with respect to 3, so now 3 will go down, 4 will go up. So if 4 go up, naturally the right child of 2 become 4, whose left become 3, and right is obviously remain 5. And if you calculate the balance factor now, we have to calculate the balance factor also. So let's calculate this. This is for 0, for 3 also 0, for 1 also 0, because they are leaf nodes. For this 4, it is 1 minus 1, that is again 0. It is for 2, it is 1 minus, now it is 1 2 or maybe 1 2. In either side it's ultimately 2. That means 1 minus 2 is 1. Sorry, minus 1. Now you see, after correcting this part, automatically, as just I said some minutes back, that maybe it happened that the lower level node balance factor automatically corrected, and the same thing happened over here. You see, now after, maybe in this situation we had 2 nodes unbalanced, but correcting only one actually corrected other node also, and it may not happen also. It totally depend upon the structure of the tree. So now the situation is something like this. Now what I can do? I can try to incorporate 6 in this particular tree, right? So let's do this. Let's do in this side. So your new formation after inserting 6, obviously it will be inserted here. So new formation will become 2, then 4, In this side we have 3. In this side we have 5. In this side we have 6. So that means you see now the balance factor of all these nodes are, this is for 0, this is 0, this is 0. Balance factor of 5 is 0 minus 1, that is minus 1. Balance factor of 4 is 1 minus 2, that is minus 1. Balance factor of this one is 1 minus 1, 2, 3, right? So 1 minus 3, that is minus 2. So now see, including 6 has violated the balance factor of the root, only root. That means I have to correct it. And we can easily see that ultimately, I mean, uh, in this is a situation where you have to do the rotation again, right? So that means if we see what part is heavy, right subtree is heavy again, and right part of the right subtree is heavy. So left rotation is required naturally. Now left rotation in the set, left rotation with respect to the unbalanced node, something like this, right? Now see, here a confusing situation will arise, because if you pull down these two, 4 will go up, that is fine, but you cannot connect 4 in the left of 2. The reason is that the left of 4 is already busy with 3, right? But I have to connect these two. So that means what to do? How, if I connect this 2 with 4, then where this 3 will go? Actually, in this situation, the actual rule is, let's draw it here. The actual rule is that obviously 4 will go up and 2 should down. So with respect to that previous cases, always do one, you can do one thing blindly, that is 4 will go up and left of 4 will be always whatever was done, whatever was parent of 4, that is true, that is true. This will happen. Now question is that where 3 will go. So I am coming it very soon. And when 4 go up, obviously the other right side of the 4 will go up. So, and they will remain untouched. So right of 4 is 5 and right of 5 is 6. Now, and obviously this left part of 2 remain untouched, so this become 1. And always remember that in this type of situation, where when you are rotating something, if you rotate with, say left rotation, at least with respect to this example, when you are doing a left rotation with respect to a node, if the right child of that node have a left child also, you see, let me tell you again, when you are rotating a node, rotating a tree with respect to a node, if the right child of that node, that is 4, have a left child also, then what we do, we actually connect the left of this 4 as a right of the parent, that is 2. So 3 will come in this side, because with respect to the nature of the binary search tree, 3 is lesser than 4. That's why 3 always will be less in the left side of 4. Now since left of 4 become engaged with 2 because of this rotation. That is why we have to connect this previous left child of 4 as a right child of 2, because when you are rotating, right child of 2 become blank, that you can connect. And you see, the binary search tree rule has been maintained, because when you are connecting right of in the right of 2, ultimately since 2 is in the left of 4, that means 3 is in the left of 4, and it's maintaining the property of BST. Because why I'm saying property of BST, because ultimately we can say that AVL tree is a balanced binary search tree, right? So now if you take the uh, balance factor, if you calculate the balance factor of all the nodes, it is 0, this is 0, this is 0, these are leaf nodes, this is -1, this is 0, and this is 1 2, and this is 1 2, that means 0. So you see, at the end of the incorporation of all the key values in the AVL tree, it remained balanced. It is now balanced. So this is a correct AVL tree. Also, you can say it's a balanced binary search tree. So if a set of numbers is given to you to create the AVL tree, you have to do in this way. But you should write in between these two as what actually you have done. Like you are inserting 2, here you are inserting 3, like this. So you should maintain whatever change you are going to do in every side. That I have not written because I am just showing you how to do it. Now obviously this set of numbers can be given in any haphazard order. So according to that it will happen. But since it is only in increasing order, that's why what happened, only a particular case has arisen, that is right subtree right heavy. But it may not be true. It may happen that sometimes right subtree right heavy, sometimes left subtree left heavy, sometimes right subtree left heavy, sometimes left subtree right heavy. Anything can happen. So according to that, you have to, I mean, you have to change your, you have to connect and rotate if required. So this is an example that we have just discussed. So